Hello, students. It's Mr. Rich. We're going to do another math homework Q&A. I got some questions that have come in, and I'm going to jump right to it. The first thing we're going to do is it looks like some pre-calc. So this is a review for Unit 3A, which I think goes up through maybe 3.7 in the AP pre-calc. So, well, what I'm going to do here, I'm going to take a look at this first question. This actually comes, yeah, this one comes from 3.1. But here we're looking at a periodic function. You can probably tell that looks like a cosine function, but the period is 8, right? It takes 8 units of along the x-axis for it to go through one period. So the period is 8. Now, what I can tell is that from 0 to 4, the function is decreasing. And then from 4 to 8, it's increasing. And they're talking about what's it doing 20 to 24. Well, one thing that I can do, if I know that it is increasing 0 to 4, every k period after this, it's also, so I could say 0 plus 8, because the period is 8. Period is 8. So plus 8 from 0, let's do it this way. So from 0 to, so if we come back over, it's going to be doing it again here. So 0 plus K8, 8K, and then 4 plus 8K. So when K is 1, it's going to be from 8 to 12, decreasing. When K is 2, it'd be the next portion of the period. And then we could say the same thing over here. We could say 4 plus 8K and 8 plus 8K. And we're talking about increasing or decreasing, right? So I could set, say, this 4 plus 8K equal to 20. That's going to take me, so 20 minus 4 is 16. 8 divided by 16 is 2, right? So when K is 2, let's do it when K is 2. When K is 2, it's going to be decreasing from 16 to 20. And when K is 2, it would be increasing from 20 when K is 2 to 16 plus 8, 24. So yeah, I'm showing that it is going to be increasing on that interval. All right, the measurement of an angle in its position is listed. In which quadrant is the terminal ray? So we don't know what quadrant that's in. Well, the way that I know that is that I know that that is half of a pi. That's 1 pi. That's 1.5 pi. And that's 2 pi's over here. So that's well beyond 2 pi. So I'm going to subtract 2 pi and it becomes 4.6 pi. So that would be coterminal to 4.6 pi, which would be coterminal to 2.6 pi, which would be coterminal to 0.6 pi. 0.6 pi is second quadrant. It's right between 0.5 and pi. So that's what you'd be doing there. You probably want to put that into a positive. So if you add 4 pi, which would be 2 counterclockwise rotations, that puts you at 1.7 pi. That negative 2.3 pi is coterminal to 1.7 pi. 1.7 pi is going to be in quadrant number 4 over here. This is quadrant 4. So it's in between 1.5 and 2. All right. Now, what I want you to do, Reagan, take a look at those pages that you sent and tell me, and you don't have to tell me right away because I'm going to do a problem for Taylor, but tell me which sheet you want me to go to next, because I may not get to all of them. I just want to know which ones are the most important to you and do them in that order. And we'll go over to Taylor. All right. Wow. Is that right? That score is 24 to nothing, and it's almost halftime. Man, I'm glad I didn't waste my time watching that game. Next. There we go. All right, using the U substitution, using the substitution U equals, I guess that's X plus 1, I guess is what they're saying. Yeah, okay, that would make sense. If I use this here, Taylor, as my U substitution is what they're asking me to do, then what would that look like after we complete the U sub. So let's try it. Oh yeah, I see. You know what? This is actually, I think, very similar to the problem that I was doing where we had, it was called the change of variable. What happens is when we let u equal x plus 1, du is dx. When we then go to construct our new integral, this is going to be the square root of u, and then dx is du, like that. But you can see that by doing my substitution of u and for dx, I don't get rid of the x that's on the top. But I can fix that by actually taking the definition of u and solving that for x and calling x u minus 1. So this becomes now the integral of u minus 1 over square root of u, which is u to the 1/2 du. Now, that's a much better scenario for me, and for this reason, because I can split this up into two separate fractions. This could be u over u to the 1/2 minus 1 over u to the 1/2. And when I simplify that fraction over there, that thing is right in the wrong place right there. Can you believe that? I'm going to have to move that over a little bit. There we go. It was right on top of the button that I needed. Yeah. So anyways, that's going to be then the integral of u to the minus 1/2. No, u to the 1/2, because it's 1 minus 1/2. So that's u to the 1/2 minus u to the minus 1/2 when I use the negative exponent rule right there. I think that's as far as they wanted us to go. Yeah, I think that's going to be it right there, Taylor. That's how we got there. Okay, next. All right, thank you, Reagan. I'm going to do that. First to our second page, number 7 and 8 on the second page. Well, let's do that. Each figure below gives a circle in the XY plane with center at the origin and an angle theta in standard position. Find the value of each expression. Well, what we know is that sine of theta, when it comes to circles, is going to be the y coordinate divided by r. And that's simply because we know that sine is the opposite side divided by the hypotenuse. And when you take a look at what we have here, if you were to make a right triangle here with the x-axis, the opposite side from this reference angle, I'm using this reference angle with the negative x-axis right there, the opposite side is the y-coordinate, negative 7.375, and the hypotenuse happens to be 8. It's the radius of the circle. Now, the reason that we don't use y over r on a unit circle is because r is 1. And so the sine of the angle is just whatever the y coordinate is, because it'd be y over 1. But in this case, all we have to do to find sine of this entire angle is take the y coordinate and divide it by 8. And that's going to be our answer right there. Cosine is going to be the x coordinate, right? Because that would be the adjacent side, while the radius right here is the hypotenuse, and therefore the cosine of that angle is going to be a negative 3.1 over 8, and tangent is y over x, which would be a positive 7.375 over 3.1, like that. Right, there are two negatives and they will cancel each other out. Right, so that's kind of all it is to that, and very similarly you could do number 8 right there. Let me jump over to the third page, Reagan, which I think is this one. In the XY plane, the terminal ray of angle theta in standard position intersects a circle of radius r at a given point. What are the values of theta and r, with theta being between 0 and 2 pi? Well, this right here is telling me that this is a on a unit circle, but a unit circle that has been scaled by a factor. Okay, now, what is the scale factor? I guess what I'm going to do, the way that I like to look at this is realize that the scale factor was 12. In other words, they took a point that was on the unit circle and they scaled the circle by 12 and made the radius 12. How do I know that? Because this has to be root 3 over 2, and this would have to be a 1/2. So I know that the radius is 12 right here. And then that would tell me that the original point when I scaled it back to the original radius of 1 would have been this point right here. And that's what I'm going to use to find theta, because the question is, where on the unit circle is that ordered pair? And that ordered pair is going to be in the second quadrant. So it's over here. And it's going to be this point right here. This is the point that hopefully you have memorized or have some sort of a scheme by which you know what the ordered pairs are within the quadrants of the unit circle. So that's the point there. And I know what that angle is. That angle is 2 pi over 3. That. Okay. So that's the easiest way to do those, Reagan. I would just do the scaling, right? Kind of set that. You can ask yourself, what did you multiply 1/2 by to make it into a -6? Okay. How did I know it's not 1/2 and it wasn't a 1? When do I see root 3s, right, on the unit circle? It's when they're paired with a 1/2. It's a root 3 over 2. So anyway, so that's what told me the scale factor there was going to be a 12. Next, we're going to go and do a calculus. We have a definite integral from 0 to 4 of x over x squared plus 9. We are going to try u sub on this and let u be the x squared plus 9, which means du will be 2x dx, which tells me dx is du over 2x. I'll construct my new integral. This will be the square root of u. There is an x right here, but the dx gets replaced with du over 2x. The x's are gone. I do have a 2 in the denominator that I will pull out as a 1/2. I will call that u to the minus 1/2 du, because that is u to the 1/2, but I use the negative exponent rule to bring it up as a u to the 1/2. Now what I'm going to do here, Taylor, I am going to transform these limits of my integration, which are x values, and change them into u values using my definition for u. When x is 0, u is 9. So my new limit is 9. When x is 4, that would be, it looks like a 25. 4 squared plus 9, 25. We'll go ahead and take the antiderivative of u to the minus 1/2. I have this 1/2 sitting here. That would be u to the positive 1/2 divided by 1/2, or 2u to the 1/2 evaluated from 9 to 25. To make to make my life a little easier, I'm going to bring the 2 out to the front. 2 times 1/2 is 1. So it really is just u to the 1/2, 9 to 25. That's 25 to the 1/2 minus 9 to the 1/2. Raising a power to a 1/2, that is 1/2, is a square root. That is 2. Now, let me just show you something here, Taylor. I did want to mention this, and maybe, Taylor, you could give me an answer to this. And if I asked you this last week, I apologize, because I've asked this to so many people, I forget who I've asked. And I haven't got a real good answer. I think I have an answer. The question is this. When you take your AP exam, both of you are taking AP exams, AP Pre-Calc, AP Calc. Have you been told that you're going to be taking it in Blue Book, which is the College Board testing app that they use for the SAT? And have you been told that you are going to have access to Desmos, the graphing calculator, on the calculator section of the test? Has your teacher told you anything about that? Either one of you? No? And yeah, that's usually what the students are telling me, is that the teachers haven't said anything about it. But I Googled it, and I couldn't find it anywhere on the College Board website. But I did find out that, yeah, apparently I am sure that you are taking it in Blue Book. So your multiple choice should be totally Blue Book. But when it comes to the free response, you will be delivered the questions on the screen in your Blue Book app, but you will be writing in a test booklet that'll be handed in and manually graded by the graders. But I have seen online that it looks like you will have access to Desmos. So you have the option of using your TI-84 or pulling Desmos up. So I would say if on the calculator portion of the test, Desmos is not bad when it comes to integrals. So they would certainly not give this problem to you, Taylor, on a calculator active section. But let's just see what Desmos would look like what the problem looks like in Desmos if we were to do it. So if I go to the functions portion and come down to the calculus portion, there is an integral. So it does numeric integration. So I can tell it to go from 0 to 4, and I can say x over root x squared plus 9 dx. And there's our answer of 2. So it does the numeric integration faster. Okay, right there. So it's not a bad idea. And hopefully your teachers, when you get into the month of April, when you come back from spring break and you're prepping heavy for your AP exam, maybe you all will be exploring some of the ways that you can use Desmos to your advantage on the test. But the thing about it is on these AP math exams, you're really not under a time constraint and rushed, maybe like you would be on the SAT. So Desmos really can play a role when you're taking the SAT. But as far as saving you time, if you know how to use your TI-84, you're probably better off sticking with it. But the more that you learn Desmos, the better you're going to be at using it, and could use it maybe on your SAT test to more efficient and effective use. But just a thought, I'm pretty sure you are going to have Desmos at your disposal on the calculator portions of your test. All right, back to Reagan and AP Pre-Calc. All right, so I kind of covered those, Reagan. How about on the fourth page? What is of interest to you on the fourth page? There's some graphing there. I can talk about some of those. Sure, 30 and 31, let's do that. All right, so I'm going to give you my take on graphing these functions, 30 and 31. These have all the things, right? These have the vertical stretch, they have a phase shift or horizontal shift, and 31 also has a vertical shift. Well, the first thing that I do recognize is that number 30 is a negative sign function. It does not have a vertical shift. So the very first thing I'm doing is I'm putting my midline on the x-axis because of no vertical shift. The amplitude is 3, so my max and min lines are going to be at 3 and -3. So I like to put those lines on there as guides as I'm graphing this. Now, one thing that we want to do when we're trying to determine the phase shift here is we need to factor out that coefficient of the x right inside the parentheses. So I'm going to rewrite this function. I'm going to factor out a 1/2, right? Because that's x over 2 is 1/2 times x. So I need to pull that out, which would make this x minus pi over 2, or I would say 2 pi. When you factor out that 1/2, you have to divide it by 2. No, wait, why is my mind playing tricks on me? No, if you factor this out and you divide it by 2, my brain all of a sudden just kind of factoring out, you're dividing by a 1/2, which is the same as multiplying by 2. Yeah, so -2 pi. All right, so we got everything we need there. We do need to calculate period. The period is 2 pi over 1/2, which means the period is 4 pi. So what's happening here is we are doing a phase shift, and I'm sorry, Reagan, that's a positive, right? It's x over 2 plus pi, so that's going to be plus 2 pi. Given that the period is 4 pi, the phase shift is 2 pi to the left. It is half of a period. It is half of a period shifted. But let me show you what happens. I'm going to start sine. I'm going to graph what this would look like. My reference points for my plotting would look like if I was doing no phase shift. And remember that the period here is entire 4 pi. So this whole -2 pi to 2 pi is one complete period. Sine would start at its midline. It is a negative sign, so it's not going to open up like this. It's going to open down, and after the first fourth of a period, it's going to go to the min line, right? And pi is 1/4 of the period, and then it would return to the midline after the next quarter period. That means going back this way, it would go up to the midline, and then after the next quarter period, it would return. So you can see that that's what it would look like if there were no phase shift. But the phase shift is 2 pi to the left. So what does that mean? If you shift this thing 2 pi to the left? Well, think about where this 2 pi, if I'm going 2 pi to the left, it's going to come back to this spot right here, okay? And then this spot here it's going to come back over here. So really what happens is that when you do a phase shift by half of the period, you are basically reflecting it back across the y-axis. And so this thing is really going to be looking like a positive sign. And it's going to go like this. It's going to come up here and come back down. And it's going to come back down here and come up like this. Okay. So phase shifting by half of the period is the same as changing the sign of the coefficient in the front. It's the same as reflecting it across the x-axis. Because think, if you take any sine or cosine and you shift it left or right by half of its period, you have reflected it across the x-axis. So that's 30. Let's go and take a look at 31. And Taylor, if you have another one, go ahead and send it in. Here, our midline is going to be at -1. Our amplitude is going to be 2. So there's going to be our max and min lines right there. We are going to factor out the 2. That is the coefficient in front of our x. So we have 2 cosine of 2 times x minus pi over 2, minus 1. Like that. So our period is going to be 2 pi over 2. So you got to remember 2 pi over b is our period. So it's 2 pi over 2 pi is our period. So that means pi over 4 is our quarter period. So one of the things I'll mention to you, Reagan, that you want to know for your next coming up, and maybe you know this, but every time a sine or a cosine moves a quarter of a period left to right, it is always transitioning from a midline to the max or midline to the min or vice versa. It's always doing that. Over 1/4 of a period is when it's going to be jumping from the max to back to the midline or from the midline to the min or vice versa. And the reason that's important is what you're going to see on your summative. I have no doubt, like getting off track here, I'll come back to that problem. But what they like to do is they like to give you portions of a period. For example, let's suppose I showed you just this portion of a sine wave. And the only thing that I really showed you is that this is 3 pi over 4. And you've got to get the period of this thing. Well, that's 1/4 of the period. From the midline up to the max is 1/4 of a period. So how do I get the actual period? I would take the 1/4 of the period and multiply it by 4, because there would be 4 of those to complete one complete period. So the period has to be 3 pi. So just keep that in mind. If they show you, another thing that you've probably seen this in some of your AP classroom work, if all they show you is that, and that says 4 pi, right? The period's 8 pi, because now I know that I'm looking, when I go from one midline crossing to the next midline crossing, that is going to be 1/2 of the total period. So period is going to be 8 pi in that case. Back to this problem, our period is pi. And it's shifted down. Now, before I am going to then plot my points that I would be plotting if there were no phase shift to the right of pi over 2. Cosine starts at its maximum, so it would be starting up here. And our quarter period is going to be a pi over 4, right? Because if the period is pi, coming out to here is one complete period, then pi over 4 is a quarter period. So it would go from here to the midline, here, back to the midline, next quarter period up to the max line. So that would be one complete period of cosine without the phase shift. But then what's happening is the phase shift is causing everything to go to the right by pi over 2. Excuse me, by pi over 2. So this line right here, and by the way, that is half of the period, right? Pi over 2 is half of the period pi. But what happens is each of these points, I'm going to go ahead and shift them over to the right, pi over 2. That one goes there. This one is ending up right here. This one is ending up here. This one is, the point here is coming over to here. This point is over to here. So then you can see what is happening. This is going to come back here, here, back to the midline, up here, and so on and so forth. So it's coming down, coming up, back here, like that. Okay, and you can see that that also is basically a reflection around the it's a reflection around the midline. Because if we were to draw what was going to be the original function, it would have looked like this. That was without the phase shift, so on. So it was a reflection around the midline. I got another one that I'm going to work, Reagan, that I don't know if it's on the last page there, but it's the tabular one where you have to come up with the model equation based on tabular data that would fit a sinusoidal waveform. All right, this one I'm going to do with U sub here. We could get away without U sub, but I'm going to go ahead and use U sub. So I let U equals negative 4x. Du is negative 4 dx. So when I make my substitution, it is going to be e to the u, and dx would be du over negative 4. So that's going to be a negative 1/4 du, right? Because I just substituted in negative, I substituted negative du over 4. I will change these units. So since x is 0, if x is 0, u still is 0. If x is 1, this would be a negative 4, like that. Well, the antiderivative of e to the u is e to the u, right? It's itself. So it's negative 1/4 times e to the u from 0 to negative 4. So this is negative 1/4 times e to the negative 4 minus e to the 0, which is 1. And if you distribute to match it to the answer over there, you would want to distribute that negative 1/4. So it'd be negative e to the negative 4 over 4 plus 1/4. Changing the order of those gets you the answer D right there. 1/4 minus e to the minus 4 over 4. Okay, let's do one more. Okay, this looks like another U sub. We'll start with u being 1 plus sine theta. Du is, the derivative of 1 is 0, sine's cosine. This works out perfectly, right? D theta is du over cosine theta. So when I build that integral, it does become the square root of u here. When I stick in du over cosine theta, it will knock out the cosine theta. It just leaves me du. Now, I'm also going to make a transition here, Taylor, to the variable u on my limits. When x is, or excuse me, theta is 0, sine of 0 is 0, and so u becomes 1. When theta is pi over 2, sine of pi over 2 is 1, 1 plus 1 is 2. So now this is not even in the realm, it's not even the realm of trig, right? I'm not in sine and cosine. I'm in u at this point with just algebra. So I'm going to go from 1 to 2. I will call that u to the negative 1/2 du. Antiderivative, add 1, divide by that. That becomes 2, u to the 1/2. I would evaluate that from 1 to 2. 2 times square root of 2 minus 1, right? 2 goes in there. 2 to the 1/2 is the square root of 2. 1 to the 1/2 is 1. There you go. That's how it works. So u sub makes that pretty handy. Yeah, okay, I see that, what you sent over, Reagan. I'm going to pull that up. Suppose you are riding a Ferris wheel. After everyone is loaded, the wheel starts to turn. The ride lasts for 105 seconds. Your height in feet above the ground, anytime t is modeled by that. You do not need a calculator for those except the last two. What is the period? It is 2 pi over b. B is the coefficient right here, pi over 10. So it's 2 pi over 10. Keep, change, flip, it's 20. Now 20 what? Well, it asks us, what does the period represent? Well, remember, in this case, our x-axis variable is time in seconds. So this is 20 seconds. Right? You mustn't forget that period is a horizontal distance. It's a horizontal, okay, of whatever that x variable is. In this case, it's t, is time. So period is the time it takes for it to go one cycle. So what does the period represent? It represents the time it takes for the Ferris wheel to make one complete revolution. That's what it represents. Now, frequency is 1 over the period, 1/20th. Now, this is where some students struggle, like, oh, 1/20th, what does that mean? But look, if you say that the period is 20 seconds, and it is, it's 20 seconds per cycle. Or we could say it's 20 seconds per one revolution of the Ferris wheel. Well, what is the reciprocal of that? The reciprocal of that is literally 1 revolution every 20 seconds, which means if you divide 1 by 20 and get 0.05, yeah, it's 20 seconds for 1 revolution. Yeah. So this becomes 0.05 revolutions every second. So what is the interpretation? It's 1/20th. The Ferris wheel turns 1/20th of a revolution every second. If you wanted to put that into degrees, what's 1/20th of 360 degrees? 18, right? 18 degrees. So if you're taking a look at the Ferris wheel, it would be rotating 18 degrees per second. That's the speed at which it's rotating, if you want to call it that. The circular speed, angular velocity, they call it. But so what does frequency represent? It means there's 0.05 revolutions on the Ferris wheel every second. What's the maximum height? Well, the maximum height is going to be the midline plus 50. So that's going to be 115 feet. The minimum height will be the midline minus the amplitude, 15 feet. How many circles will the Ferris wheel make during the ride? Well, the ride lasts for 105 seconds. So I would take those 105 seconds and divide it by the fact that it takes 20 seconds per one. Sorry, it takes 20 seconds per 1 revolution. So 105 divided by 20 is 5.25. It's going to do 5.25 revolutions. How high are you when the ride stops? I would do this on my TI-84, but I'm going to do it this way instead. I'm going to type h of x is 50 sine pi over 10 x minus 4 plus 65. And then it says, how high are you when the ride begins? That's called h of 0. What's the height at time 0? 63.903. Now, I got to make sure that I am in radians mode. I have a feeling that I put myself in degrees mode. Whoops, up here. If you hit the wrench up here, yeah, need to be in radians mode. So I start at 17.447. What is your height when the ride stops? Well, that's 105 seconds. My height would be 80.4508 right there. Okay, any questions about that, Reagan? I'm going to show you this one because I think you're going to see one of these. So they give you a table. It says the following data could be modeled by a sinusoidal function. Use the data to answer each problem below. Well, to estimate the period, I'm going to find successive maximums. So I'm going to come over left to right. There's my first maximum. Then I'm going to go until, and this table wraps around, right? 9 to 10 to 11. So now I'm going to come around to where my next maximum is. It's like it's right there. So that means the period's 10. 17 minus 7, right? That's the x distance for it to go through one peak to peak. So that would be 10, and then the frequency be 1/10. The midline, right? The thing that you want to know here, Reagan, about midline and amplitude is your midline is always going to be your max plus your min divided by 2, because your midline is the average value or the halfway point between the maximum y and the minimum y. So it's max plus min over 2. It's all you got to know. But when you do the amplitude, it's max minus min over 2. So I'm going to find my absolute highest value, which was 52, and my absolute lowest, which I believe is -11. Yep. So I'm going to come over here and do 52 plus -11. It's 41. Divide that by 2. 20.5. Amplitude is 52 minus -11. That's 63, right? That's the distance between the high and low on the y-axis, 63. So we do 63 over 2 is 31.5. Now we can make a sinusoidal model. The amplitude is 31.5. And I'm going to use a sine. And here's what I'm going to do to use a sine. I know that my B coefficient will be 2 pi over the period. 2 pi over 10 is pi over 5. But there's probably a phase shift that I'm going to put in here. I know that the midline is 20.5. right there. Now, how do I find the phase shift? My midline is 20.5. So what I would do is I would go left to right until I find the first closest value to the midline right here. That's at an x equals 5. So that, because the reason I'm looking for the first point closest to the midline is that's where sine starts. It starts at its midline, but it didn't start at the midline until x was 5, so it's shifted to the right 5. So that means this has to be x minus 5, and that's it. And you would find that if you shoved all of these 20 data points into Desmos or your TI-84 and you ran a sinusoidal regression, it'll return a somewhat close value to these. Okay, that is that. Ooh, all right, Reagan. That doesn't look too bad. I will throw that one up there. Or not Reagan, that was Taylor. Okay, so from looks of it, it's going to be a U sub. So we'll go with U is 3x squared plus 5. Du will be 6x dx. And so dx is du over 6x. Okay, so I have an x up here. I now have a square root of u. The dx is du over 6x. The x's will cancel. The 6 in the denominator will come out as a constant at 1/6, leaving me u to the minus 1/2 du. So I bump up the exponent by 1 to make it 1/2. I divide by that or multiply by 2 plus c. So it looks like it's 1/3 times the square root of 3x squared plus 5 to the 1/2. It is, because that's a 1/3. That is indeed, well, it's the square root, but just to the 1/2 power. Not too bad. Okay. Well, ladies, I hope that was helpful. We still got time if there's more that you want to go over. Reagan, what about you? Or we can call it an early night. Okay. Well, if any of you are taking tests, good luck this week. Hope you have a wonderful week. Keep studying hard. Remember, it's better to do a little bit of math every single day, like 15 minutes a day, than to like not do anything for 3 days and try to cram a bunch of stuff in. So little by little, that's going to get you to where you need to go. It'll help you on your retention quite a bit. But anyways, that's it for me. See you next Sunday night, 8 o'clock. Good night, everybody.